Thank you very much for introduction, and it's my great pleasure to participate in this conference, and it's my fourth and third time I participate in this conference. I really grateful to organizers for organizing such a nice event in such difficult time for Ukraine. And I'm bonded to, I'm attached to Odessa. I grew up in Odessa. I attended an Odessa National University as an undergraduate, a graduate student, and I knew personal Professor Sinikov and Professor Hula and Professor Wiesing. So it's really great opportunity for me. Thank you very much. Let me share my screen. I tried to be consistent with the subject of the conference and to present something which is of geometrical and nature and algebraical same time flavor, which seems to me very great kind of directions to which this conference is developed, deviated, started with geometries and analysis and now algebra. And I would like to present some, it's a kind of summary of my, not only some, but I would like to present a method on the example of one interesting problem which we have been working for a while, actually for many years. And this team is myself, Dmitry Mitryshin from Odessa Polytechnic, and Walter Trebers from Darmstadt, Germany. So the problem is the following. So the motivation came from 1916, basically, when simultaneously and independently three kind of problem popped out in the air. So given the non-negative trigonometric polynomials, even odd with this special normalization, and algebraical polynomials, which is univalent in D. Univalent means one-to-one in unit disk. Find the sharp estimate on absolute value of modulus of the coefficient. All coefficients are real. In this case, in complex case, we can consider complex coefficient, and this is totally different, much more subtle, much more difficult situation. But even for real case, in this case, we don't know anything, really anything. We don't know the sharp estimate for the second coefficient. So all A's in our case are real. And sharp is keyword here. It's important. So we're really interested in sharp estimate of these coefficients. So this problem is completely solved. And we know that coefficients AK here bounded. It's like the sharp estimate is 2 times cosine something. And in absolute value, I mean, all of them turns out to be non-negative, as far as I remember, at least for the first several. And the extremizers are known. In this case, only the sharp estimate for A2, for absolute value of A2, A3, AN, and in odd case AN minus 1 are known. There are no sharp estimate known for A4, A5, etc., until the very last one, right? And in this case, nothing is known, absolutely nothing. So, but why 1960? Let me give you an idea. In that case, two papers appears, one by Ludwig Biberbach, one by Leopold Fejer. So a few words about the reason, motivation for the problems. So in geometric complex analysis, one of the central moment is kind of an object which is typically used to test some statements or make some conjecture, is so-called Kirby function. The Kirby function is this function which has this expansion. So what's remarkable about that function? It has the largest possible coefficients, which I will mention later, and in absolute value, and it has the largest possible, in some sense, image of the unit disk range. It contains the value at -1 is -1/4. So I'll show you this is a range. So it's a slit domain, and there is a disk of radius 1/4, which is in this. And there is a famous Kirby 1/4 theorem, which says that with this normalization, any analytic and one-to-one function in the unit disk, so-called Schlicht function, has the image contains the disk of radius 1/4, and 1/4 is sharp, and why it's 1/4 you can see why it's sharp. It's here, it's shown on this picture. Actually, Kirby didn't prove this statement. He proves that there is some disk of radius, fixed radius, and the Kirby function, I mean this function, gives estimates that this disk cannot be more than 1/4. And his student Ludwig Bieberbach proves the estimate for the second coefficient of Schlicht function, and proves that the absolute value less or equal than 2 in complex case. And from here he derived the statement that this disk is indeed radius 1/4. And this illustrates the importance of estimates. And it's considered to be a difficult, important problem. The extremal estimates for the coefficients. And these days, maybe the interest is not as great as, say, 50 years ago, but still. So this is you see, it's, I just insert, this is the first page of this famous Bieberbach function. And here is the estimate A2 equals 2. And the famous Bieberbach conjecture was the driving force for the 75 years of development of geometric complex analysis, which says that perhaps the coefficients, the estimate for coefficients is less or equal than n. Here it's just very innocently looking simple footnotes statement. So first of all, it states that because of Kirby function, the estimate should be greater or equal than n, and then it says that perhaps it is n, and that's it. So no great importance in this statement. It's just kind of by the way statement. And that surprisingly that this innocently looking comments became a famous Bieberbach conjecture. And it was solved, and it was solved in 1981 by Louis de Branch, and he proves that yes, indeed, coefficient, the estimate is an is n, and unique extremizer is up to rotation in complex cases Kirby function. So in 1969, Ted Suffrage suggests polynomials, which looks like this one. Pretty simple. If you modulo this term, if you drop it, it will be just classical Fejer polynomial, which has this property. So it started with the decomposition, and very important this property, an 1 over n. In coefficient in polynomial world, if the polynomial is 1-to-1, the last coefficient cannot be large. It should be at most 1 over n. And it's a totally different story, because in Kirby function, n's coefficient is n. And here the last coefficient is 1 over n, small. But this is the largest coefficient which you can imagine. And for this polynomial, there are nice properties. So it's -1, it is -1/4. And the coefficient approaches k if n goes to infinity, which means that in sine problem, the absolute value of coefficient grows, while in cosine problem is bounded by 2. And it's in some sense it's a surrogate for Bieberbach, for Kirby function, because if you consider all real coefficient polynomials which are univalent in the unit disk with this normalization, these coefficients are the largest one. So it's like Kirby function Majorans for functions, but this is for polynomials. At the same year, it's actually it's even half year earlier, there were published another paper, also kind of very influenced for the mathematics. It's paper by Fejer, and this is the first page. And in this paper, Fejer considers, introduces very powerful idea, which is now called Fejer's representation of non-negative trigonometric polynomials. And namely what? He noticed here that if you write non-negative trigonometric polynomial in this form, if it's possible, this is a good question. So as a the value, absolute value squared of the standard algebraical polynomial on the torus, on the unit circle. And in this case, if it's possible, then coefficients lambdas for the, and mu's for these non-negative trigonometric polynomials are related to the coefficients of these gammas. Gammas are coefficients of algebraical polynomial in a tricky but observable way. So these are quadratic forms, you can see. So this way, if you want to use, if you want to find the optimal estimates for the coefficients lambdas and mu there, you can employ methods of quadratic optimization, which were available at that time. It's kind of Rayleigh type theorem. And using these ideas, he obtains the following statement. So if you have a coefficient, a polynomial, trigonometrical even polynomial started with 1, and then the estimate for the first coefficient is this one. You see 2 times cosine, so the absolute value is bounded by 2. And he found the extremal polynomial in this form. So it's a polynomial, algebraical polynomial with nice coefficients, absolute value squared on the unit circle. If you restrict z to the unit circle, there's normalization factor. And here, for example, this is the optimal polynomial. So this is the largest non-negative. This is non-negative trigonometric polynomial with largest coefficient, and it's unique. And here there is a corollary which says that, for example, for this type of polynomial, this is root of 2. So this is a non-negative trigonometric polynomial with the largest second coefficient, which is root of 2, and it's unique. And then Echevarria and Sass, 10 years later, they found the estimate for the sharp estimate for all other coefficients in cosine polynomials. And this is an extremizer they wrote in this form. And then the extremizers for the second coefficient were rewritten nicely, and there is a compact form of this coefficient, and there is a coefficient form if you write in this way, and in some books they call Fejer-Korovkin polynomials. And so we are done with sine, and so we are done with cosine, I'm sorry. And we have an idea about what's going on with univalent trigonometrical, univalent algebraical polynomials, right? In 1950, there was a paper by Rogozinski and Segal. So first of all, it turns out that for sine, the estimate of the coefficient less or equal than k is just trivial, it's just one-way statement, which implies, of course, that if you have one-to-one polynomial with real coefficients in the unit disk, then the estimate, this Bieberbach estimate is trivial in this case. And it's an easy case for polynomials. And there they notice that they consider general problems. So they consider non-negative trig polynomial, non-negative on 0 pi, of course. With normalization here, they put 1 and get the estimate. Absolute value of B2 less or equal in odd case, this nice, beautiful statement. And in if n is even, this is an ugly sum, like 2 cosine, and this is the root of some polynomial. And the proof is very kind of smart, nice, short. They use Lucas theorem about non-negativity of algebraical polynomial, but they made the comments. So to find extremizers, you need to consider kind of characteristic equation, and they say that in general, however, the method based on this equation is not easily adaptable for obtaining explicit result, in particular when n is large. And later you will see why. And we take efforts and spend many, I would say even years, to get to working on this problem. And here we finally we found the extremizers for this case. So this is a compact form for extremizers. This is trigonometric polynomial which is extremizer in odd case, and it's unique. And this is a trigonometric polynomial which is also unique for even case. In odd case, we found the coefficients, but they are really ugly. In even case, we were not able to find the coefficients, unfortunately. But we were, it's surprising, I mean, for us at least, that we were able to find the compact form, the closed form of the polynomial without finding the coefficients, which is kind of irrational. So here are the coefficients. We state it in a little different way. Namely, we consider typically real polynomials. Typically real polynomials are polynomials which are real for real and maps upper half plane to upper half plane. And you can characterize it in the other way, that if imaginary part in the upper half plane is non-negative, that it's typically real. So it's an equivalent problem to find something for non-negative signed polynomials, or to find the estimate for coefficient for typically real. Why typically real? Typically real are much nicer than univalent polynomials. And any univalent polynomial with real coefficient is typically real polynomial with proper normalization, right? But what's the problem with univalent polynomials? The sum of two univalent polynomials might not be the univalent polynomial, while the sum of two typically real polynomials is a typically real polynomial. So people who are working with in this area, they prefer to do something with typically real polynomials, which implies that this statement, an estimate is valid for univalent polynomials with real coefficients. And very often, surprisingly, the extremal polynomial turns out to be univalent with non-negative coefficients, which is phenomena which is needed in explanation. And you see how tricky the coefficients looks like. So U sub j's are Chebyshev polynomials of second kind. I will tell you later what they are, and perhaps you know. And these are the values at these points for this cosine. So these are numbers, and these are numbers, and they're different if parity is different. So these are coefficients which we have found in odd case. And we have found the compact form, closed form for this polynomial, but in a very interesting way, as a sum of two rational functions. Surprisingly, it turns out that to work with rational functions, it's more kind of doable and pleasant than to work with polynomials. There is some advantage in rational function, and so you see it's nicely looking two rational functions, and that give us the estimate about the size of the image of the range of this polynomial, and which is important in applications. And it's computable, say, for small and here, say, for if it's cubic polynomial, and you can easily find that this cubic polynomial is a cubic polynomial with the largest, which is typically real, with the largest second coefficient, which is 1, and which is when the smallest second coefficient, which is -1. And now about the method. So we switch to upper half plane, and we know that image is positive. Trig polynomial negative, then we factor out one sign, and what's left is cosine. So it looks like the problem for cosine, however, the normalization is different, and it's a different problem. And there is nice relation between A's and gammas. And so A's are initial polynomials, gammas are for these intermediate cosine polynomials. And because it's non-negative, then we were able to we can write it in this form. And this is famous Fejer lemma, which says that any non-negative trigonometrical polynomial can be written in this form. So we use this lemma applying to this trigonometric polynomial. And the coefficients, of course, gammas and deltas related in a tricky way, like a quadratic form. And because the first coefficient is for z is 1, we have here 1. And we are interested in the estimate of A2, the estimate of this guy. So afterwards, we came up with a problem like that. The estimate for the second coefficient is the maximum of this form subject to this form is equal 1, and the minimum correspondingly. And or you can write in this form like maximum or minimum using a matrix presentation for this quadratic form. And then the general theory says that if lambdas are roots of equation of this form, then A is between the largest one and the smallest one. So these are kind of generalized eigenvalues, if you want. And so the problem now, A is this matrix, is you see it's a Toeplitz matrix. Looks simpler, and this looks simple Toeplitz matrix. However, the problem, say I scale instead of x and put here 2x, you get this matrix. And this is 7-band matrix. You see, it's a 7-band matrix. And the problem is the following. You have to find the roots of this equation. So it's a determinant of n by n Toeplitz matrix, which is pretty kind of tricky sense, right? It's n by n matrix with this x. So the determinant is, even for small n, it's a polynomial of huge degree. And this is what Rogozinski and Segur warned that even for large n, we run into really tremendous algebraical difficulties. So now I switch from geometry to algebra. So the problem now is to determine the roots of this equation again. So this is 7-banded Toeplitz matrix, huge, n by n. So the determinant is a polynomial of huge degree. And we have to find the roots for roots of these specific polynomials. Really not a piece of cake. And the only hope and what we knew about the situation, and perhaps this is the only what we knew so far about this type of problem, is polynomials, Chebyshev polynomials. Because This is the definition of Chebyshev polynomials. But there is a nice, remarkable formula which says that Chebyshev polynomial can be written as a determinant of this three-band matrix. Nice matrix, and this is, if you write this determinant, of course, it's a polynomial of also n by n nth degree, and you have to do something with this in general situation, in general form, nth degree polynomial, But here is a specific polynomial, Chebyshev polynomial, which has a trigonometric presentation. So roots of this expression are known and kind of widely in use. And we know all the roots. And you can see here is cosine. These are roots of the polynomial, of Chebyshev polynomials. And the largest root drops out in the estimate of Rogozinski and Séguin. And this was a hint of us that what we can do use, should be somehow Chebyshev polynomials involved. But how to involve it, we didn't know. We spent many efforts, many months, years to find what's the determinant of that crazy matrix. And finally, we were able. This is mainly the central result of that paper. And maybe some by itself, it's an interesting and a quite valuable statement. The determinant of this seven-band matrix, this crazy matrix n by n, could be written in this form. If n is odd, this is a product of Chebyshev polynomial and its derivative. And if it's even, here we have this expression. So for many years, we tried to use only Chebyshev polynomials, and it didn't work. And then at some moment, it was really Eureka moment, we decided to try the derivative of Chebyshev polynomial, which we never seen before people employ this subject. And turns out that finally we found a way to employ that. It's just amazing. And because the roots of polynomials and derivative, roots of polynomial derivative in Chebyshev case alternated, so in this case, we get n odd is this expression, and if it's even, we get this expression, and now we were able to find the roots. Do I have any time left, or how much I have, or I took all my time?
Yes, we have some time.
Okay, so from there, which means that I found the eigenvalues generalized, right? But to find all the other coefficients, I have to find eigenvectors. And that's another non-trivial problem. So given these eigenvalues, to put it back to that crazy matrix, and to make this characteristic equation, and then these eigenvalues, eigenvectors, one of them again, give us coefficients deltas in presentations of Fejer representation, and then from deltas you have to go to gammas, and then from gammas to a's. And deltas we were able to find in these terribly looking formulas. Gammas in even case we couldn't find it, but what's interesting, a's are difference of gammas. So even, in odd and even case, we couldn't find gammas. But in odd case, the difference of gammas we were able to find. And this way we found a's. So the extremal coefficients for the coefficients for extremal polynomials in odd case. In even case, we failed to find coefficients. However, we were able to find the closed form, compact form, which is amazing, which again we didn't expect. So here's the even case. So in even case, again, we were able to write the polynomial as a sum of two rational functions with some parameters which are computable, and you see this as sum of two rational functions. And there is this parameter. Let me don't spend my time with this. So in case n equals 2, if you do this, we obtain two polynomials of this form. So we obtain the polynomial as the sum of two rational functions. And these two rational functions are this. Again, not a piece of cake. You see, even in case n equals 2, they're kind of quite unpleasant. Maybe not very much, but again, highly non-trivial to write this way. And surprisingly, if you add them to, then the sum will be z plus 1/2 z square. So this is a quadratic, typically real polynomial with the largest coefficient here, which is 1/2. And this is with the smallest coefficients, 1/2, right? So to summarize, I should say that working with this in direction what Fejer suggested, we discovered that there are kind of some interesting phenomena and some interesting kind of way to work with the polynomials as presenting them as rational functions. But we are working with typically real polynomials. So there are early ideas like that in works of Manfred Brand, but it was in about 1980s and it didn't develop it further. They were not developed further. And another coefficients which are left are A3 coefficients. And recently we were able to make the progress, and looks like we have sharp estimates for A3, and this is just an announcement. Thank you very much for your attention, and glory to Ukraine.
Thank you very much, Alexander. Let us to thank our speaker.